Welcome to the second lesson in the Engineering Design Process series. My name is Denny Davis. I'm a retired engineering education professor. Today I'll be leading you in a discussion about game strategy and how to define needs from this strategy. Why game strategy? First of all, what is a strategy? Strategy is simply a plan of action to accomplish a goal. When we're talking about robot game strategy, it's a plan to win, or at least to perform well in a robot match. Well, why is strategy important? First of all, strategy defines what we expect a robot to do, where we want it to go, what feats it must accomplish, what conditions it must withstand. And second, if we're thinking about being considered for some of the judged awards in FTC, strategy is an important part of what's considered for the Think Award, the Innovate Award, and of course, the Inspire Award. In a general way, a strategy is simply a utilization plan. It defines what a design product must do. So therefore, if it's a robot or any other design product, it's clearly important for designing what our design solution must be able to do. What goes into defining a game strategy? The considerations include what the paths are that the robot will be expected to execute, what scoring attempts we will make. Even the order in which we make these attempts will be important. The likelihood of our being successful in any attempt, the time required for each scoring attempt, and alternatives when conditions change and we need to change our plans. So overall, a strategy is really putting together multiple options for play that will depend upon the uncertain game conditions. We need to be ready to perform regardless of what surprises occur on the game field. An important part of strategy development is calculations. The goal of a robot game is to score the maximum points in the time that's available to us. So, what is it that determines the probable points in a single attempt at scoring? Well, two things. One, the points possible if we're successful, and second, the probability of success we have for that type of scoring attempt. We calculate or estimate the probable points simply by multiplying the probability of success times the points possible. Example would be, if we're attempting a 20-point score and we have a reputation or an expectation of 75% of the time being successful, then the probable points for this particular way of scoring is 75% multiplied by the 20 points, which means 15 points is the probable points, the average number of points we would expect by this type of scoring attempt over some period of time. Another important parameter we calculate is the probable points per unit of time. The probable points per unit of time is the probability of success times the possible points divided by the amount of time required for that scoring attempt. So, if the scoring attempt that we listed above takes 10 seconds, the probable points would be 75% times 20 points divided by 10 seconds, or 1.5 points per second. This gives us a measure of the efficiency in scoring, how quickly we're able to score points. So, what are the probable points then to score in 30 seconds if we use this scoring method? We take the probable points calculated by the probable points per unit of time multiplied by the amount of time available. This means 1.5 points per second times 30 seconds gives us 45 points. So for that 30-second period, we could expect, on average, to achieve 45 points with this scoring method. So this scoring efficiency is the points per unit of time, probable points per unit of time. So let's get more specific. Let's look at a hypothetical game. We have shown here a layout for scoring. There are 20 rings initially scattered on the floor. The robot may possess one ring of its own color at a given time. Points are then scored by placing that ring around a peg or under the table, and the number of points is as shown. The robot must score from a position behind this black line, so staying on the near side here of the black line. Now, there's also a possibility of 10 bonus points if we have 2 consecutive rings of our color over the same peg. 10 bonus points. So let's look at some scoring attempt efficiencies for the different options we have available for scoring here. If we're trying for a 1-point score, we see that we have a 90% probability of being successful. That tells us that the probable point for 1-point attempt is 0.9 points. 90% of 1 point, so on the average, 0.9 points. We similarly could calculate the probable points for the 5-point score, 10-point score, 20-point score, 30-point score. So on average, those are the number of points if we try scoring those different pegs. What about the probable points per unit time? For the 1-point attempt, that's the probable points is 0.9 points divided by the time, which is 5 seconds, or 0.18 points per second. Similarly, we can calculate the probable points per unit time for the other scoring options available to us. And notice that the 0.18 was the lowest. The highest end up being for the 10-point or 20-point scoring attempts. So on a per unit time basis, our best chance of getting points is going for 10 points or 20 points. Now, there are times when we need to combine probabilities because we're going to be scoring multiple times or attempting multiple times. Now, if we're attempting to score in independent attempts, in other words, success in one doesn't affect whether we're successful in the next attempt, then our probable points is simply whatever the probable points was for the first attempt, plus the probable points for the second, and so on. An example is find the probable points if we first try for 10 points and then try for 20. How do we do this? Look at the table and see that attempting to score 10 points. On the average, we'll get 7 points. Attempting to score 20, on the average, we get 10. So really, those 2 attempts, on the average, we could expect to earn 17 points. 7 plus 10, 17 points. Now, if, on the other hand, we have 2 attempts and they are dependent, in other words, scoring one of them depends upon our success in already having scored the other one, then we calculate the probable points differently. The probable points is the probability of the first one being successful. times the probability of the second one being successful times the number of points that we would gain from getting both of them. So an example is, remember, we could get 10 bonus points if we have consecutive rings on a peg. So let's say we had 10 bonus points that we're trying for on a 20-point peg. We'd score 20 points and then attempt to score the second 20-point score. We have to have both of them in order to get the 10 points. So what are the probable points from our attempts at getting this bonus? That would be the probability of the first is 50%. You see that from the table. Second attempt is also 50%. 10 possible points if they're both successful, which means on the average we're going to have 2.5 points. So only a quarter, 25% chance of that 10-point bonus. So then in that case we would have the probable points for the first attempt, which would be 10, probable points for the second attempt 10, plus whatever the bonus is, on the average 2.5. So we could say that our probable points for those two attempts that would depend upon one another would be 22.5 points. Now let's look at a similar case where we're attempting to score in a 30-point peg. Notice that we have to be successful getting, yes, we scored ring number 1 30% of the time, but then in the second ring there's only 30% chance that the second ring would also be successful. So multiply those two percentages together and we get 9%. So less than 10%, 1 chance in 10 that we would get the bonus points when we're attempting to do that on a 30-point peg. So let's define a game strategy now that we see that we can calculate probable points. Let's say that we have 15 seconds remaining in the game, 1 ring in hand, and we have to decide what do we attempt to do during that 15 seconds. Looking at our table, 15 seconds, we could try for 20, 10, 5, or 1, but not 30. All right? So which of those is going to give us the highest probable points? The 20-point peg. So from this information, we could make a strategy decision for that 15 seconds. Let's look at a 45-second period of time. And let's look at 3 different options. Let's say we have a choice between trying for 30 points, then 20, and then 10, or trying for the 30-point peg twice, and assuming that we won't get a bonus, or see what it would be if we got the bonus as well. Probable points for the 30, 20, 10 is simply adding up the probable points for a 30, and then a 20, and then a 10. They're independent of one another, which gives us 26 probable points. We look at trying 30-point twice. The probable points for a 30-point attempt is 9 plus 9. For the second attempt, that's 18 points. If we are hoping to get the bonus as well, we get the 9 plus 9 plus, remember, 0.3 times 0.3, which is 0.09 times the 10 bonus points. We end up with 18.9. Not much better, so options B and C are about the same, and it doesn't make that much difference in our scoring. All right, assuming that you're able to come up with a strategy then, whether it's for 15 seconds, 45 seconds, or some other period of time, we need to document our strategy. Remember, if it's not documented, it's not done in the eyes of people who read your documentation. So let's identify strategies that we might consider. That's the first step in documenting. What are the strategies you're going to consider? Show the probable points for each of those. So do the calculation, show those probable points, and then choose and explain why you chose one of those strategies. So let's take a case here. Let's say we had 60 seconds of game time that we're going to use for scoring on these pegs, and other game time for other kinds of scoring. We have three different options we're considering. Option A, B, and C are different strategies. And we look at each of those separately. For option A, 3 attempts, 30 points, 3 times the 9 points, probable points per try, gives us 27. Notice that that takes the full 60 seconds, so if we are a little slow, we'll only have 2 attempts, and so on. And if we're really fast and we do it well, we could get 2 possible bonuses. Let's look at option B, 4 20-point attempts. 20 points, probable points for each attempt is 10. That gives us 40 points. Note that it would take 56 seconds, so we have a little bit of leeway there so that we potentially could be successful on those 4 attempts. Notice with 4 attempts, we could even possibly get up to 3 bonuses. Let's try to look at the 6 10-point attempts. 6 times probable points, which is 0.7, gives us 42 probable points. It would take the full 60 seconds. We have the chance for 5 possible bonuses. So with this information, we've documented strategies considered, probable points for each, and considerations we had in mind. We make a decision and we document that as well. Our choice, strategy C. Of course, this has to be okayed by our alliance partner, not conflicting with what they're doing. Our choice is made because it's the most points possible without bonuses, and we have up to 50 more points possible for bonuses. Note also that if we're scoring 10 points, think back about the field. We could score from the left side or the right side, which gives us some flexibility there in terms of the game position when we're attempting these scores. So that's good as well. So here we've documented our strategy. It can be understood by others. We can justify our strategy by the probable points. Now we have defined strategies, but what is it that makes a strategy useful to us? Well, first of all, what is it that's required for a strategy to be of value to us? It must be accurate in the estimates. If it's not accurate, then we're basing our decisions on poor information. So our probabilities, our times to score, these need to be well-founded. Good estimates give us accurate estimates for our strategy. And secondly, our strategies should provide flexibility when it's needed. We need to have strategies in hand for those unexpected conditions that could occur. Now, how might a good strategy help our team? Well, first of all, developing a strategy is going to prepare our drive team so they have a common understanding of what they're doing, and they'll be working together in a unified way. Second, having a good strategy in hand aids us in communicating with our alliance partner. They know what we're planning to do because we can explain it well. And third, our strategy then defines needs for the design of our robot. And fourth, as mentioned before, strategy enhances the opportunity that we have for being awarded one of the judged awards. Now note that defining needs is the next step in our design process, so we'll keep that one in mind. So Why do we define user needs? We have our strategy in hand. Why define needs? First of all, defining needs provides a record of what the users and the designers of our robot are expecting, what they believe that they need. Sometimes they have different perspectives, and here's a way to get consensus and clear understanding of one another's perceptions. Secondly, our needs give us a simple portrayal of what the solution is going to be that we're going to develop. It's a first picture of what we're going to produce. Third, our list of needs serves to prompt us when we are generating ideas for our solution. And fourth, our needs become a basis for comparing the merits of the different ideas that we do generate. Where is it that we're going to see these needs appearing so that we know where to look in order to define our needs well? Well, when we're competing on the game field, for sure, but also when we're using our robot, such as in demonstrations to the public. Another time might be when we're ordering and fabricating, when we're assembling and testing, when we're being judged for an award. Each of these times when a robot is being discussed or used, there can be needs that surface that we need to be aware of. So in general, important needs could appear throughout the life cycle of the robot. We need to think about how the robot is being used and what the needs are associated with that use. I like to categorize needs into 4 different categories so that we don't miss something important. First of all is the functional needs. What are the features and functions of our robot? How fast does it need to move or accomplish things? How far does it reach? What size limitations we have? Certain performances, repeatability. There are also technical needs in terms of the soundness of our engineering design, how sturdy it is, durable, strength, etc. So we need to make sure we don't overlook those types of needs. Thirdly, there are needs associated with the resources that we use in developing this robot. The number of motors, servos, sensors, these kinds of resources could raise additional needs that we need to keep in mind. And fourthly, there are human needs. Value is delivered to the people who use the robot, who observe the robot, who value the robot. We need to know what the needs are, how easily that can be used, controlled, its appearance, safety. There are human needs. So let's look at each of these in order. Notice that these needs span the game, but also other uses of the robot. So let's not forget that. For functional needs, let's think about that scoring, ring scoring that we talked about earlier. And what are the functional needs here? We could identify things like the collection speed, the travel speed in getting to from the point of collection to the point of scoring, time, scoring speed, the reach, the height, scoring success. Each of those could be a need that we need to consider as we develop our robot. Notice that some of these actually come directly from the strategy information. We said we were attempting to score 10 points in 10 seconds. So therefore, the summation of our collection speed, travel speed, and scoring speed needs to be within this 10-second limit. All right. Also, we had said that we expected 70% success rate in scoring on that 10-point peg. So therefore, that needs to be one of those needs that we specify as a functional need for this ring scoring system. What are some of the technical needs? Well, how much load needs to be lifted, the weight of the assembly, the stability of the delivery for scoring, the durability of the parts, which means how long before the parts might fail. Something like electrical discharge, static discharge could be an important need. So these types of needs could be specified as technical needs. What resource needs we identify? Well, number of motors. When we look at the entire robot, we're limited to a certain number of motors on the entire robot. Here we're allocating, saying only 2 motors max would be available for this ring scoring system. Number of servos, again, this could be affected by the number of ports we have or something, or the servos we have available. The sensors, perhaps limited by what we have available and what we have the competence to be able to program and use. Parts delivery is very much affected by whether these are standard parts. Machining takes a lot of time and resource. Spare parts, okay, do we have a system that will stand up so well that it's rare that we need to replace a part? If that's the case, 1 spare would be adequate. If we have parts that fail frequently, we need more spares. But in this case, we could specify 1 spare would be adequate for these major parts. Now, human needs. Let's think about that. What kinds of things might be specified? Well, the operator needs to be able to see the collection of the ring. So we want the ring to be visible when the collection is taking place. Control, the operator is trying to control the robot. We need a function to be such that the operator only needs to control 1 action at a time, and not several at one time. Feedback, the operator needs to know when the ring is collected so they can begin moving. The appearance of safety, ejection, all right, you can only have 1 ring on board. If a second one gets on board, can you eject it quickly? And here we're defining a need for quick ejection. All right, we have a list of needs of these 4 different categories of needs. We list them in a table such as this. We begin to identify which of these are of high, medium, or low importance to us. High here is defined as something that's going to greatly affect scoring, or our credibility in the eyes of judges and competitors, or it's going to have a major effect on overall performance. Medium would be lesser amounts in these areas, and low, little effect. So we first review these and, as a team, define which of them would fall into this high priority grouping. You come up with that decision, identify which ones are high priorities. Similarly, medium priority, identify which of those, and the remaining ones would be the lower priority. We could then regroup these so that all the high priority ones are together, all the medium priority ones are together, and the low priority ones. This then provides a basis for us to begin identifying solutions, knowing what's going to drive it the most. The high priority needs would most heavily drive our idea generation and looking for characteristics of the robot that are going to make it successful. Medium priority comes second, and we would hope that some of these low priority ones also are going to be brought to bear on our decision making. Notice that these priority needs will provide focus for us. We can't look at all these needs at one time, so we give our greatest attention to the higher priority needs and then move down correspondingly. So in summary, we have a game strategy. We need a strategy that's going to give us the most points in the time available. We need to identify alternative strategies for limiting conditions that are going to occur. We need to assess the accuracy of our estimates so that we know that our strategies are based on good information. Some of this will come by just good guesses, some will come by doing some testing to get good values for scoring success and for time to score and so on. With the game strategy defined, our design needs should be identified because these must support those game strategies and other possible uses of our robot. They must address what the robot must do, the functional needs, its soundness, the technical needs. Must address the rules and other limitations of our team, which deals with the resources, and our stakeholders and their needs, so those are the human needs. And note, we must document well the game strategy and the design needs, because as I've said before, if it's not documented, we have no proof that we did it. So therefore, in our documentation, we should show the steps we've taken and the reason for those steps, and provide a clear record of the outcomes from these various steps. The record of our needs and our priorities would be the final outcome from the steps that we've discussed today. So, to this point, we've talked about game strategy and defining needs. In our next session, we'll start talking about generating ideas and screening those ideas, and then in subsequent sessions move through the rest of the process. Appreciate the collaboration we have between Robo Raiders and Ex Bots who are participating in this lesson series. As I've mentioned before, these lessons are based on lessons within the second edition of the Pre-Engineering Primer in Chapter 8. And these videos will be on the Robo Raider YouTube channel, which are referenced from my VerityDesignLearning.com website. Thank you for all of your attention. Thanks to FIRST, who has provided this inspiring sporting event for the mind. We look forward to seeing you again in our next lesson.